Hello guys, and welcome to the last problem that we are going to be solving on power series, and you are given problem number 3. We have solved problem 1, problem 2, where I explain and laid a very good background on power series, and now I'm going to go on to the last question which I have extracted from one of your exam papers. Now if you want to solve the third one, solution, of course, given 1 minus x squared, d squared y by dx squared, and minus 5x dy dx minus 3y equal to 0. If you want to solve this particular differential equation at the point x equal to 0, which is our usual point, I observed that this differential equation has a lot of minus sign, and I don't like minus signs. Minus signs are an inherent part of mathematics, but I don't like them, so I always look for a way to take them out of my way if possible. So I'm going to multiply through by minus 1. Okay, I'm going to multiply the whole of this differential equation through by minus 1. So in multiplying this whole differential equation by minus 1, it will reverse the position of this, making it x squared minus 1 d squared y over dx squared, then plus 5x dy dx, then plus 3y equal to 0. So very good. Now that I have it like this, I can now convert the form to this. So it's still equivalent to us having x squared minus 1, then I have this as my y2, that's the second derivative, plus 5x y1, the first derivative, then plus 3y, that's the 0th derivative. I can put 0 here. Is that okay? Now I have it like this. The next step is to differentiate n times. So differentiate n times. If you are differentiating n times, this is how it's going to be. So we'll start with this term, okay? Then we'll go to this term, we'll go to this term. Remember the rules. Which term are we going to use as our u? Very good. We're going to use this one as our u. So the one you use as your u is this guy. So as usual, the first combinatorial coefficient is 1. Okay, so then the nth derivative of this is yn plus 2. Remember, you've already differentiated this one 2 times. So when you now want to differentiate it n times, it means that the total number of times of differentiation is n plus 2. So when you differentiate your u n times in the first case, you're not going to differentiate your v. You just leave it like that, x squared minus 1. Okay, so that's the first case. And you now put a plus. Then the second combinatorial coefficient is actually n. Okay, that's your n combination 1. Is the second combinatorial coefficient. N combination 0 is first, n combination 1, n combination 2. This is 1, this is n, and this is n minus 1 over 2 factorial, and so on and so forth. So you keep adding combinatorial coefficients until you exhaust this guy over here in terms of like the one that will get you to 0. Now, when I put the first combinatorial coefficient, I'm going to reduce the order of differentiation by 1. Instead of differentiating n times, I'll differentiating it n minus 1 times, and this will make it n plus 1. So just remove 1 from this one like this. So if you differentiated this one a lower order, you now have to differentiate this one 1. So you differentiated n minus 1, then you need to differentiate this one 1 times. So this one you differentiated it n times, and you differentiated this one 0 times. So n plus 0 is n. So for each terms, as I said before, when you add the number of times you differentiated each u or each v term, it should give you n. So I differentiated u in the second case n minus 1 times. I need to differentiate v once, so that n minus 1 plus 1 will give me n. Differentiating this one once, you're going to get 2x. Are we good? And we now have plus. Finally, we have the third combinatorial coefficient, which is n minus 1 over 2 factorial. Then I'll now differentiate my y, reduce the order, or in other words, just subtract 1 from this place. Then when I now differentiate this one, this is the n minus 2th derivative of y. Okay, so when you differentiate this one, n minus 2 times, that's y2 plus n minus 2, cancelling out gives you n, or you can just subtract 1 from this and you still get the same thing. You have to now differentiate your v 2 times so that it can be balanced. N minus 2 plus 2 will give you n. So differentiating this guy 2 times is still the same thing as differentiating this one 1 times. So if you differentiate it, you get 2. So remember what we said, once your v gets to a constant term, that's where you stop. You stop expanding. Okay, so we've satisfied the derivative, the nth derivative of this first term. Okay, then plus, I'll put a big plus, then I'll now go to this term. So differentiating this term n times, of course my u is this and my v is 5x. Okay, my u is y1 and my v is 5x. So my first combinatorial coefficient is 1. Okay, then I'll now differentiate this one n times, giving me yn plus 1. Okay, then I'll now put my v without differentiating it, which is 5x. Then in the second instance, my second combinatorial coefficient is n. Then I'll now differentiate this one n minus 1 times, or I'll just remove 1 from here to now be what? Yn. Okay, then you now differentiate this one once. So when you differentiate it once, you get 5. So what are you supposed to do at this point? You're supposed to stop, because we have gotten to a constant in v. Is that okay? Then we're done with this one. Then finally plus the last term is 3y naught, and if you differentiate 3y naught n times, we'll get 3y, actually what? N. So 0 plus n. The 3 is not really affected in this case, and everything here is equal to 0. So this is the nth derivative of this particular differential equation. Now after differentiating it n times, we're now going to put x equal to 0. So in putting x equal to 0, let's observe what happens. Any term that have x will cancel out, such as this term. So this term is disappearing. Again, this term is disappearing. So we can now put what we have. I mean, 1 times this is actually yn plus 2. Okay, there is actually what? An x here. So it will be 0 minus 1, which is minus 1. Okay, take note. There's an excess, so when you put x equal to 0, 0 minus 1 is minus 1, and plus. We now have 2 cancelling out, 2 factorial is 2. I'll just be left with n minus 1 yn. Then coming over to this term, I'll have plus 5 times this is 5n yn, then plus 3yn equal to 0. Right? Then you can now see that your minus yn plus 2 is still the same thing as minus. When you take the whole of this one to the other side, it's going to be minus, open bracket, n minus 1 yn, and plus 5n yn plus 3yn. This was not pretty cool of me, but you can still understand what I'm trying to do. So yn plus 2 is equal to, factoring out yn, you have n minus 1 and plus 5n plus 3, everything will be on yn. Somebody else can still simplify this. Yn plus 2 is equal to, you can see that n is common in these terms, so you have n is common, then you now have n minus 1, then plus 5. Okay, and plus 3, like this, yn. So when you solve, you get your yn plus 2 as n minus 1 plus 5, it's plus 4. So you have n plus 4 and plus 3 yn. And this over here is our recurrence relation. So the nature of the recurrence relation is true for n greater than or equal to 0. In this case, we can solve for 0, 1, 2, 3, 4, 5. Okay, so we're going to solve for these 5 points and see what we're going to get if we discover a pattern. So I'm going to copy the recurrence relation, and I'm going to go to another part of the page. So let's do that. All right, so there we go. Now we now want to start getting our terms. Remember what I said, after you put the points x equal to 0, this yn plus 2 is not just the n plus 2 derivative, it is now the n of n plus 2 derivative at x equal to 0, which is fn plus 2 of what? 0. Okay, so that's what it means. It is now like an initial condition for the n plus 2 derivative, and so is this guy over here. So let's use different values of n to iterate so that we can get our solution. So we'll start with when n is equal to 0. When n is equal to 0, you have your y2, that's 0 plus 2, is equal to 0 times this whole stuff, 0 plus 3 y naught. So you now have 3 y naught. Okay, so our y2 is equal to what? 3 y naught. Are we together? Now let's go to another point. When n is equal to what? 1. So let me just be writing my yn plus 2 is equal to n plus 4 plus 3 and a half yn. So this was our recurrence relation. So when n is equal to 1, if we put 1 here, we're going to get y3 is equal to, so you now have 1 times 1 plus 4. 1 plus 4 is 5. So 1 times 5 is 5. 5 plus 3 is 8, right? So you now have 8 y1. N in this case is 1. So let's go to when n is equal to 2. So we are actually covering up gradually. When n is equal to 2, you now have your what? Y2 plus 2 is 4. And you now have 2, then into 2 plus 4. 2 plus 4 is 6. 2 times 6, 12. 12 plus 3, 15. So you have 15y, and n is 2 in this case. Are we together? So let's move to when n is equal to 3. So when n is equal to 3 in this case, so what are we going to get? I'm still going to bring this one down so that I can remember. Yn plus 2 is equal to n plus 4 plus 3 all on yn. So when n is equal to 3, when we plug it here, we're going to get y3 plus 2 is 5. So 5, then you now have 3 as n. 3 plus 4 is 7. 7 times 3, 21. 21 plus 3, 24. So you now have 24 y3 here. Are we good? So let's finally check out the last value when n is equal to 6. So when n is equal to 6, so what do we have? We now have what? I jumped. Not the last value though. Around 4. So when n is equal to 4, we'll have y. 4 plus 2 is 6 is equal to, you now have 4, right? 4. So 4 plus 4 is 8. 4 times 4, 16. 16. Are we in 4? 4 plus 4, 8, right? Then 8 times 4 is what? 32 plus 3, 35. So you have 35 y, and this point is 4. Are we together? So we are now in the last value of our iteration, and after iterating 5 times, we should be able to discover a pattern. Okay, so for n equal to 5, what's it gonna be? So when you plug in 5 here, you're going to get y5 plus 2, which is 7, is equal to 5 into 5 plus 4. 5 plus 4 is 9 times 5, 45 plus 3, 48. So 48 y5, like this. So at this point, we have exhausted our iteration variables. Then we can now start figuring out some patterns. So we have our y2 as 3y0 and our y3 as 8y1. Now our y4 is expressed in terms of y2, and I can still call it y4 is 15, then y2 is actually what? 3y0, which I'll write as 3 times 15y0. So everybody knows that 3 times 15 is 45, but we're not going to do it like that, okay, because we want to find the pattern. So let's check this one out. So you have y5 expressed in terms of y3, which is also expressed in terms of y1. So you now have 24. Instead of y3, I'm going to write 8y1, and this will be 8 times 24 y1. Okay, so thankfully we don't have negative signs in this one, so we're good. So y6 expressed in terms of y4, and y4 has already been solved to this. So you have 35, then 3 times 15 y0, which evaluates to 3 times 15 times 35 y0. Then finally we have 48y5. y5 has already been evaluated to this in terms of y1. So you have 48 and 8 times 24 y1, which gives me 8 times 24 times 48 y1. Now it makes sense because I discovered that anytime we are on 7, this last term is the product of the term below 7 and the term after 7. 6 times 8 is 48. Now check it out, the pattern still repeats. When we are in 6, 35 is the product of 5 and 7. Okay, 5 and 7, which is the number below 6 and the number above 6. When we are in 5, 24 is the product of what? The number what? Below 5 and the number after 5. 4 times 6 is 24. So when you write your numbers like this without multiplying them, it helps you to find the pattern. So now that we've gotten our y1 from y1 up to y7, we can now write our solution, our Maclaurin solution is given to us as y is equal to y0, of course, then plus x y1 plus we have x squared over 2 factorial y2 plus x3 over 3 factorial y3 plus x4 over 4 factorial y4 plus x5 over 5 factorial y5 plus x6 over 6 factorial y6 plus x7 over 7 factorial y7. So I'm stopping at x7 because I did my iteration until I got y7 and plus dot dot dot. So let's start replacing the values now. Remember, all these things, they stand for initial condition at the point 0. So y0 at 0, y1 at 0, y2 at 0, y3 at 0. y3 at 0 means the third derivative at 0 is that key. So that's your Maclaurin series. So your y in this case is now going to be what? Your y0 stays as it is, it's arbitrary. Then your y1 stays as it is. Then for y2 now, let's go and see what y2 is. y2 is 3y0. y2 is 3y0. So I'm going to have plus 3y0 all over 2 factorial, and I have my x squared and plus. Let's see what y3 is. y3 is actually what? 8y1. 8y1. Then instead of y3, I'll have 8y1 over 3 factorial. Then you now have what? x3 and plus. Now let's see what y4 is. What is y4? So y4 is a 3 times a 15 y0. A 3 times a 15 y0. So you have 3 times a 15 y0 divided by 4 factorial. This is on x raised to the power 4. I can actually guess what x5 will be. So x5 can be guessed from the value of x3. So x5 will be expressed in terms of what? x1, and I'll show you that I understand the pattern. So in x1 we had what? 8, right? So it's going to be 8 times, in x3 we had 8. So since we are currently on x to the power of 5, so I'm going to multiply the number before 5 and the number above 5, which is 4 times 6, which is 24, and to now give me my what? 10 over 3 factorial, and this is x5. So if we go and check our value of y5, we'll see that y5 is 8 times 24 y1, which I got here. So let's do for y6. So let's predict y6 without looking at what we got before. So to get y6 now, we have to refer to y4. We have 3 times 15. Then what is the next multiple now? So the next multiple is going to be times, since we are on 6, x raised to the power of 6, we need to multiply the number below 6, which is 5, and the number above 6, which is 7, to give me 35. And you divide by 6 factorial, then you have your x6. Is that okay? So let's now do the last one, and plus on x7. Okay, let's confirm x6. So x6, I forgot to put the y naughts. Sorry, remember the y naughts there. X6, just like we said, is 3 times 15 times 35 y naught. So for x7, let's do x7 together. So to get x7, we need to refer to x5. So the coefficients in x7 will have these terms, 8 times 24, only that since you're dealing with x to the 7 now, then the multiple will now be what? 7 times what? 6. 7 is before 6, and 7 is before 6. Then before 7 you have, after 7 comes 8. So 6 times 8 is what? 48. So this is also a y1 divided by 7 factorial. So the pattern goes on and on and on and on. So that's the essence of writing the numbers. Okay, writing the numbers rather than multiplying them. So you can discover a pattern, and you can write infinite number of terms, just in case you want to clear your lecturers down. Now you now have to factor out what is common. Remember, anytime you solve power series solution for second order differential equation, your answer is always going to be expressed in terms of y naught and y1. That's the first derivative, and the second, sorry, the normal first derivative, which is y1, then the zeroth derivative. The zeroth derivative is your f of 0, and your first derivative is your f prime of 0. So this is y of 0 or y prime of 0. So those are the two things that will be used as the chief coefficients for your power series solution. Okay, so you have your y is y naught. We are going to collect all the terms with y naught. So y naught into 1 and plus, then we now have what? 3 over 2 factorial x squared, and plus 3 times 15 over 4 factorial. We now have x4, and plus, what is the next one? 3 times 15 times 35 over 6 factorial x6. If I want to be stubborn and put another term, I can do just that, and it will be 3 times 15 times 35 times, who can guess what it is? Since we are in x to the 8th, then we need to multiply the number before 8, which is 7, and the number before after 8, which is 9. 7 times 9 is 63. So you have 63 over 8 factorial, then this is x to the 8th. So it keeps going, plus dot dot dot. So we close the brackets. Then this is your y naught, then everything is plus y1. So you've collected all the terms in y naught. You want to collect all the terms in y1, you now have to start. So y1, factoring out from this, you get x, then plus factoring out from this, you get 8 over 3 factorial. 8 over 3 factorial, you now have x cubed, and plus the pattern now starts 8 times 24 over 5 factorial x5, then plus the next y1 term is 8 times 24 times 48. So 8 times 24 times 48 over 7 factorial x raised to the power 7. We can be stubborn and add the 9th term, and 9th term will be what? 8 times 24 times 48 times what? What do you think is going to be? Very good. If you were clever, since we are on x raised to the power of 9, the term before 9 is 8, and the term after 9 is 10. So 8 times 10 is 80. All over, you have 9 factorial, then you now have x raised to the power of what? 9. Then it keeps on going, plus dot dot dot. So this is the solution to your differential equation. Y is equal to your a, and call this one g of x, plus b h of x. So g of x is this function over here, h of x is this function over here, this infinite series, and your a is your y naught, which is your f or your y of 0, and your b is actually your y1, which is your y prime of 0. Is that okay? So this is the solution to your power series. You can stop here. So this is about power series solution of differential equations. You can try to meditate on it and solve more problems on your own. I hope you get it right, and I wish you all the best. So till the next video, stay blessed. Bye.